Hey folks, so we are doing one more problem from chapter 12. It's number 70, and it reads a 750 gram disc and a 760 gram ring, both 15 centimeters in diameter, are rolling along a horizontal surface at 1.5 meters per second when they encounter a 15-degree slope. How far up the slope does each travel before rolling back down? So it may be a little bit tricky to visualize what to do in this scenario. By the by, I have sketched out a really rough but quick drawing showing basically what's going on here. We have our two objects, a ring and a disc. Both the same diameter, rolling up this hill, moving at the same linear speed, translating speed. The general strategy for this is not to be thinking about forces, not to be thinking about torques, but instead to be thinking about energy, right? To be thinking about energy. So what, for a general strategy, general strat is going to be to convert all of our kinetic energy, right? The total kinetic energy, not just rotational, not just translational, but our total kinetic energy into our gravitational potential energy. All right. So, because that's going to tell us how high we can actually get in the vertical direction, not even talking about if we think about torques and forces, we're going to actually have to figure out something about, the length of the hill, and it becomes just a lot harder, if not impossible, to actually solve this thing. So let's start off. With our disk. How about our disk? All right, we're going to have our disk, and then we'll have our ring somewhere over here. But let's talk about our disk. Now, for both of these objects, you're going to have to look up the moments of inertia. A disk and a ring are pretty common moments of inertia, so maybe you can, jot those down or memorize them. But remember, I will always give you a table of moments of inertia, and whatever you need will be on that table. All right? So for a disk, the moment of inertia is going to be 1/2 m of the disk times the radius of the disk squared. All right? And again, this moment of inertia is actually a calculation, an integration of all the little bits of this disk relative to the axis of rotation, which is going to be in the center, right, around its center of mass. So it's a little bit trickier, right, than what we're kind of saying here. We've simplified things. That's why everything's a lookup. If you wanted to do the integration every time, I guess you could, but that's a lot of work to do that every time. So our total kinetic energy is going to be our translational kinetic energy plus our rotational kinetic energy, right? And if I think about that, I know that translational is 1/2 mv squared, and this is v of the center of mass plus 1/2 I omega squared for our rotational kinetic energy. Now there is a trick that we're going to use a lot in this problem, and anytime that we actually look at total kinetic energy in a rolling sense, we're going to keep in mind that omega is equal to the v of the center of mass over r for something that's rolling. Right, for rolling. That's a nice little trick that we can just have up our sleeve. So we can either convert the center of mass into omega, or we can convert omega into the center of mass velocity. Since we already know the velocity of the center of mass, I think it makes a lot more sense to convert this guy, the omega. So I would have 1/2, let's actually plug in our moment of inertia, 1/2 m of the disk times r squared times VCM over R, quantity squared. It's a lot of stuff going on there. Plus 1/2 m VCM squared. And let's play by the same rules here. Let's call this a big M. Let's call this a big M. Okay. So, all right. Well, I see that I'm going to have an r squared down in this denominator in the rotational kinetic energy. I have an r squared in the moment of inertia contained in the same term. So maybe I can just cancel those. And I'm left with 1/2 m VCM squared plus 1/4, I'm going to combine those, m VCM squared. Okay, so I have 3/4 m velocity of the center of mass squared. That is my total kinetic energy for the disk. Now, what I'm saying here is that this is an isolated system. Right, it's an isolated energy system, so delta E is equal to 0. That means that my total kinetic energy is going to be completely transformed into my potential energy, my gravitational potential energy. So I can say that 3/4 big M VCM squared equals big M GH. My m's are going to cancel. So it actually didn't matter what the mass of the disk was. That was extra information for us. And I'm solving for height here, so I'm going to say 3/4 times this 1.5 meters per second quantity squared over 9.8 meters per second squared. That will be my height of the disk. And what do I get? I get 0.17 meters. All right, so that's my delta y, essentially, my height. If I'm thinking about how far along, ooh, that was rough. let's get a straight line helper here. How far along my slope I'm actually going, right? I know that this height is 0.17 meters. I don't think the problem calls for this, but I think it's still interesting to figure out what is this length d here. D would be equal to 0.17 meters divided by my sine of 15 degrees, right? And so what do I get? I get 0.66 meters. 0.66 meters, quote unquote, up the slope, but a total vertical height of 0.17 meters. So that's for the disk. We're going to do almost the exact same thing for the ring now, except our ring has a moment of inertia of mr squared. Straight up. That's it. No prefactor, no coefficient out here. And the reason for that, if we think about it, the disk had mass, right? The disk had mass not only from the edge of its disk, but all the way in towards its center. So there was a distribution of mass. But if I think about the distribution of mass of the ring, the distribution of mass of the ring is all on the outside. And I drew this ring with some significant depth, some significant width here. But really, when we're thinking about a ring, we're thinking about a perfectly geometric ring where all the mass is just on this, infinitesimally thin layer on the outside. And so if all of my mass is r away from the rotation spot, I just have mr squared, right? I'm just summing up all those individual little bits, and they're all r away, so mr squared, right? So that's the ring. If I set up the same thing, k total, I'm not going to say k trans plus k rot. In this case, I'm just going to rewrite what we have. I have 1/2 m VCM squared. Right now, big M is going to be of our ring, not of our disk. We're going to find that it doesn't matter. Plus 1/2 I, which is mr squared, times omega squared, right? We're going to pull the same trick that we did before. We're going to transform omega squared into VCM over R quantity squared. So 1/2 m VCM squared plus 1/2 m r squared times VCM squared over r squared, right? And again, that's just utilizing this fun little relationship here. Just like before, my r's will cancel, and I'm left with actually 1/2 mVCM squared for both of these. So what do I get? I get m VCM squared, right? 1/2 plus 1/2 gives me just 1. Just like before, this is an isolated system, so we're saying all of our kinetic energy is being transformed into gravitational potential energy. So mVCM squared equals our mgh. M's cancel. I'm left with 1.5 meters per second squared divided by 9.8 meters per second squared. That was confusing. This is meters per second quantity squared. This is meters per second squared. That gives me my h, my delta y, of 0.23 meters. And again, we can kind of go back and figure out what that means for a distance up the ramp here. If this is 0.23 meters, d would end up being 0.89 meters. Now, if we just look at our heights are obviously, I have more height with our ring. Our ring goes higher than our disk, and it also goes further up the ramp. I mean, that makes sense because it's going higher. Why? Why does our ring go higher than our disk? Well, if they're moving at the exact same speed, they don't have the exact same amount of total kinetic energy. That's a little bit funny, but it has to do with its moment of inertia. The moment of inertia here is mr squared, where the moment of inertia here is 1/2 mr squared. And so if I think about this, I actually get half of the rotational kinetic energy in the disk than I do with the ring. As a result, I have more total kinetic energy in the ring than I do in the disk, right? So just because I'm moving at the same speed, I'm able to store more rotational kinetic energy in the ring, and that allows me to go up to a higher height with the ring. I like this problem a lot. I think this is a really good illustration of how different shapes store energy differently based on how easy it is to rotate them, or how easy it is to accelerate them, I suppose. You know, their moments of inertia. So it's a good energy problem that combines some rotational aspects to things, but also just some straight up Chapter 10 stuff. If you have questions about this, feel free to email me or swing into an office hour. Otherwise, have a good one.